Hello, welcome to O Morgan Labs, and today our problem is how long does it take for this 10-kilogram block to fall to the ground? Note, the pulley has significant rotational inertia. A lot of times people take that out and make the problem simpler, but in the real world you have inertia. So you're going to have to take into account that, or things are going to not work as you planned. So here we go. We're going to set up 3 free body diagrams. One of the 10-kilogram block, another of the 5-kilogram block, and then a third one with the pulley. All right, we're going to use Newton's second law for the blocks. That's F equals ma, or sum of the forces equals mass times acceleration. For the pulley, we're going to use sum of the torques equals I times alpha. I is the rotational inertia, and then alpha is the angular acceleration. And then the last thing, we're going to use the linear acceleration is related to the angular acceleration by A equals R times alpha. This is really the tangential acceleration related to the angular velocity. We're going to assume a direction of motion and just stay consistent with it. Don't worry if your guess isn't correct. In the end, if the numbers come out negative, that just means you need to switch the directions. But the key is to just pick a direction, stick with it until the end, and let the equations tell you if you were right or wrong. But this one is kind of simple. You can see the larger mass is going to overpower the smaller mass. Okay, here's our directions that we're going to assume everything is going. The 10-kilogram block is going to be moving down while the 5-kilogram block is moving up, and then the pulley has to move in a counter-clockwise direction. Okay, now we're going to look at the two blocks and do sum of the forces, Newton's second law. We're going to define y as positive going up. And if we look at the 10-kilogram mass, you see cables, ropes, strings, they always pull against your object. So the tension in the 10-kilogram block, tension of the cable, we'll call it T10. And then you have the force of gravity, which is just mass times gravity. And then we do the same for the 5-kilogram block. Similar setup. Okay, so when we write down everything, I put in pluses and minuses. Usually when the plus is in front of a number or a variable, you don't put it unless it's in between two terms. But this time I just did it so you can kind of see positive and negative directions. So with the 10-kilogram block, we have plus T10, because T10 is going in the positive Y direction. FG is minus because it's going in the negative Y direction. Equals mass, which is, we're just going to call it M10. And then A is negative. So the negative sign goes with the A, because you see the A is going opposite. It's going in the other direction of our positive Y. And then we set it up similar. Looks like a similar thing, right? T5 is going along the Y direction, so it's plus. Gravity is going down. It's going opposite the positive Y, so it's a negative. Equals, but this time the acceleration is a plus because we're going in the same direction as your acceleration. Okay, next we have the sum of the torques. We're going to use the right-hand rule, which gives us counterclockwise is positive. Your thumb would be pointing out if you use your right hand, and your fingers would curl the way your arrow is curling. So in this crude little cartoon, that's how you define your right-handedness, some people call it. Now, focusing on the pulley, you have your two forces pulling down on it. the T10 and the T5. And torque is distance from your center point, which is our R, times your force. So you use right hand rule, or if you can just see it visually, it's going clockwise, the T5 torque. So the T5 torque, it's negative because it's going in the opposite direction. It's going in this direction. That's negative. And now we look at the T10. It's going in this direction. Okay, you can use your right hand rule, but you can just see it. It's going counterclockwise. Counterclockwise is positive. So it's plus R times T10. And all that equals your I, which is your moment, your rotational moment of inertia, times your angular acceleration. Now, we assumed, remember, our angular acceleration was going that way. That's positive. You see it's going counterclockwise. Everything counterclockwise is positive. So we have a positive. I should have written plus right here so it would be more clear. But plus I times alpha. And there you have your equation. And then we have this auxiliary equation so we can relate the angular acceleration to your linear or tangential acceleration. And so we're going to plug in A over R where we see the alpha. Okay, now let's collect terms and solve. Here we are. So now we collect all of our equations and we count our knowns and unknowns. We know gravity and we know mass. So we know FG10, FG5. We know our masses. We know M10 and M5. We know our radius, so we know the R. We know M1. We're given that. Okay. So we're just left with T10, T5, and A. So we have 3 unknowns and 3 equations. So we have to count the unknowns in the equations. If you have equal unknowns in equations, independent equations, that means you can solve your system. Or if you're thinking about it in terms of CAD and constraining a sketch, you could think of this as a perfectly constrained model. If you have more unknowns than equations, then you're under constrained. If you have more equations than unknowns, you're over constrained. So that's a little link you can make if you've ever done CAD and done sketches. So let's continue. Okay, one thing to note here, if your mass of your pulley is 0 kilograms, this whole thing would go out and T10 would equal T5. So that's like your simplifying assumption that a lot of people do when they're taking this, when they look at this problem in like your beginning physics courses. But anyway, just a little tidbit. Okay, so we have T5, T10, and A. 3 equations, 3 unknowns. We can solve the system. And how do we do that? Well, let's find out. We could either solve it in one of 2 ways. We could set up a matrix solution. Here you would use a TI-84 calculator, TI-85, any scientific calculator, MATLAB, or even Mathematica. But most of you, I think, will be using a TI-84. I have experience with a TI-85 and MATLAB, but you can use whatever you want to solve the solution. Now, the other method is kind of by hand. You do a back substitution and then you solve for all the variables. This is the way most people do it when they're in a class or you have a test or something and they don't want you to use a calculator. You have to do it by hand. But in the real world, problems are going to be more complicated. You're going to have to use this method. I mean, this is what people use. This is what's in your computer when you solve for a finite element analysis or you're doing anything like that, because you don't have just 3 equations and 3 unknowns. You have hundreds of equations and hundreds of unknowns, and you have to have these big solver like routines or whatever. But anyway, we're going to use this way, and we'll save this method for another time. But it's straightforward. You just plug in T10 and do algebra. Okay, now, so we started here, and to make it in a form where we can plug it into our calculator, or you can row reduce. This is another way. If you're kind of fresh out of linear algebra, you can row reduce this matrix and get an answer. So that's another kind of manual way you can do it without resorting to a scientific calculator. But we go here. Notice in each column, we kind of organize things in T10, T5, and A, and then we put the constants on the right-hand side, okay, RHS, okay, left-hand side, LHS. You see that? And then we get this matrix here. And when you solve it, you get T10 is 66.45 newtons, T5 is 64.87 newtons, and acceleration is 3.16 meters per second squared, which makes sense because your rotational inertia of your pulley is going to kind of pull energy from your system, so you would expect it to accelerate slower, right? If it was 9.81, well, you know that something's wrong in your calculation. The rotational inertia is supposed to put a drag on it. So this is another subject for another video, but we'll kind of discuss energy and how much energy you have, and the potential energy gets transferred into rotational energy here, kinetic energy here. We'll discuss that later. But wait, we're not done. This happens a lot. You get into this mode of solving variables and you forget what they ask you for. They did not ask you for the tension in 10, or the tension on the 10 kilogram block, 5 kilogram block, and acceleration. They asked you how long did it take for the 10 kilogram block to reach ground. Okay, I missed a lot of problems because I forgot what they were asking at the beginning, right? Okay, that was a little glitch. I pushed the pause button. Anyway, let's keep going. You have to use your distance equation here. This is the equation you're going to use, but it comes from this general 1D constant acceleration equation. You can get this by doing integrals of the A with respect to dt, and you keep doing it, and you get basically this equation. That's another topic for another video. But you use algebra. Your initial distance, x, is 0. Your initial velocity is 0. We're looking at this 10 kilogram block here, right? That goes out. And all you have is your acceleration. Your time is your variable. And distance is just your final x. Like x is displacement, final displacement, initial displacement, all that stuff, right? So okay, there you have it. Morgan Labs. Like and subscribe.